All right, so let's go to magnetism. Right. So under magnetism, we can have magnet here with North Pole, South Pole. This can be another magnet. Okay. Now by convention, this is North Pole, South Pole by convention. This has this. Okay. So the direction in which a North Pole will go. So if a North Pole comes, it will be repelled like that. And the direction in which a North Pole will come, the North Pole will be attracted. South and North will attract. North and North will repel. South and South will repel. Okay. So if this is a North Pole, so it's repulsion. They are going to repel. Okay. There's repulsion. If it is South Pole, if here is South Pole, then what do you think happens? This is coming in. So you can have this one going like that. Okay. And then you can have that. Okay, so that is one. Now we have what actually causes magnetism, the domains, okay, responsible for the magnetic effect, okay. These are the units in a magnetic material or item, okay. If they are arranged in the same direction, then you have magnetism, okay. If they are disordered, then of course it's not. So we have some materials that can be magnetized, okay. So either they cannot be attracted by magnets, diamagnetic, or there are some materials that will have, they can be attracted by magnet, or magnetism can be induced in them by magnets, okay? But when the field is taken off, the magnet wears off. Okay, paramagnet can be attracted by magnets, okay? They have magnets. So if you look at the spin in terms of chemistry, they will have the same spin. If they have the same spin, then you can say they are paramagnets. Okay, this will allow, because the electrons are aligned in the same direction, you have a magnetic field. They will become magnets. Okay, now the ferromagnetic materials are those materials that can be strongly magnetized. Okay, for instance, iron, they can be strongly magnetized, such that when you even take the field that induces the magnetism in them away, they retain the magnetic property. So they are ferromagnets. So you have diamagnets, paramagnets, and ferromagnetic properties. Okay. So magnetism, of course, said the domains, the arrangement in the same order will cause the magnetic property. The other thing that we'll look at straight away is anytime there's a current, there's a wire, okay? Anytime current flows, electrons are flowing, or current is flowing in that direction, okay? Anytime electrons are flowing, they are flowing. When they flow, they always will have a magnetic field around them. So anytime electrons are moving, they have a magnetic field set up around them, okay? If they are stagnant, there's no magnet. But when they are moving, they set up a magnetic field around them, okay? And then there's a relation, okay? So that means current is related to magnetism, okay? Once electrons are moving, they can induce and they can set up a magnetic field around them, right? Now, how do you get it, the direction? So if this is the current, it's moving this way, the thumb rule will just give you that. The thumb in the direction of the current, so this is the current, okay? The direction in which the fingers are going will give you the field, the direction of the magnetic field, or what we call flux, or symbol denoted by phi, the symbol phi, okay? Right, so that's the magnet. So anytime current is moving, or electrons moving is the same as current, okay? Then we have the magnetic field set up, and that field you can use the thumb rule to do that, to connect that. So some also have the Maxwell screw and so on and so forth. They all give you the direction of the field around the current moving, right? Now the effect of electromagnetism. Let's look at the connection between magnets and then electricity, or current flowing and then electricity, right? This, let's look at this one. Let's say this is a magnet. The North Pole here, another magnet here with a South Pole here. You see that this is like this, it's like that, because it's going to move. And if we bring a wire here, which does not have any current in it, okay, and either relatively move the magnet, turn the magnet, or move the wire, okay. Once you move the wire, the field that is going round, that is going through the wire will be changing. That field or the flux, the magnetic flux will be changing. Once it changes, it will cause displacement of the electrons to out, so that they will arrange themselves. It will separate the electrons, okay, so that it causes separation of electrons, and that separation of electrons is what we call EMF. So an EMF will be set up in this conductor, metal conductor, okay. So far as you change the flux, the magnetic field around the conductor, which is not yet carrying current, if you change the field around it, there will be separation of electrons, okay, and that will mean EMF is set up, or current has been set up, and the current will flow. The current that flows, they have been linked by certain acronyms for us to remember. So in this case, we have what we call the Fleming's left hand rule, and then we have the Fleming's right hand rule. So just to get the verse very fast. For generators, okay, so this is going to generate electricity. Generator, that's a generator. Okay, generator, we have capital R here, 2 R's there. For generators, it is what? Fleming's right hand rule. Fleming's right hand rule. Now for motor, for you to have motor, it means you have one magnet against another magnet. So their forces are opposing, so that there will be movement. But this one, you are generating electricity. So motor is turning. This is about motion. For motor, we use Fleming's left hand rule. Okay? So the R here will tell you this is generator. And this 1R, so there's 1R motor. Okay? And you can use that to remember. So let's look at the. So in this case, we have what? Magnet, and then a conductor which is not carrying current. If it is not carrying current, it doesn't have fluid around, so the fluids are not going to interact to cause motion. So in this case, we are only generating electricity. Since we are generating electricity, it is a generator. So we use the Fleming's left-hand rule to talk about that. Okay, so let's see what happens. So from the Fleming's left-hand rule, this is how it goes. The forefinger, so this is the forefinger, this is the second finger, the middle finger, okay, and then this is the thumb, the first finger, the second finger, okay, right. So if the thumb, thumb is motion, okay, second finger, and then the first, okay, F. So the thumb must look at the direction of the motion, okay. So if this is being moved upwards, okay, so the thumb is in that direction where it is being moved. It's being moved upwards, and that's how it's moving. Now the second finger, the first finger must point in the field of the magnetic field. So where's the magnetic field? Okay, the magnetic field is like that. Okay, and the two must be the same. Let's say we are moving. Let's assume we are moving this one like that. It should not be in parallel to it. We are moving it across the field like that. Okay, so let's say thumb is that way, thumb is that way, So we are moving it inward and then out like this. Okay. So in that way, so this is the fluid is this, the direction of the fluid. So the thumb is the motion. Now my second finger, you see where the second finger is pointing downwards, then it means the current will flow downwards. Okay? So if my movement is like that, and the fluid is this way, the current will flow downwards. Alright. So that is how we can use the Fleming's left hand rule. Fleming's so I use my right hand, that's the problem, sorry. This is the left hand rule, so because we are talking about the Fleming's right hand rule as double R, so that is we use what, the generator, so that's what generator, so that's the right, we use that, okay? So let's not get confused. Double R, Fleming's right hand rule, double R, generator. So this is generating electricity. Now if it is motion, then Fleming's left hand rule, only one R in it, so that will be motor. Right. Right, so you can use that to, so this is the Fleming's right hand rule. So for generator. Now the Fleming's left hand rule will be for motor. 1 hour. Alright. So that is how you can use it to remember. So we have been able to tell which direction this will go. Let's look at how that one, the generator, we are able to generate electricity by using the turbines and Kosombo and other places. Okay. So what happens is we have a big magnet here. This is North Pole. This is our South Pole. Okay. So we would expect the fluid to go that way. Now let's assume this is our conductor passing through. Okay. This is it. Okay. So we have connected it such that it can turn and make contact for electricity to flow. Okay. For electricity to flow. Right, so let's see what happens. So we're going to generate electricity. This electricity is going to be AC. We'll come to it. We'll see how it will go. Alright, so let me just put it in before get confused. We'll come to that. Let's assume this is it. This is just a sketch of what we're going to generate. Okay. Right. Now let's see how we can apply the principles to see how things will turn. Okay. Now let's assume let's assume this is just so there is not current. Okay, we'll use the same thing for motor 2 so that you get the principle, the difference. Let's assume this is the field, and then we are moving it that way. We are moving it into the page. Okay, so because this is a generating current, we are using the right Fleming's right hand rule. Okay, generating. So we are generating. So let's see. Now we are going to turn this one. Turn it. If we turn it inward, so the thumb must go motion, and then the field is that. The field is that. Okay, the field is what we have now. So what happens to my second? The 3 fingers must be 90 degrees to each other. So they must be 90 degrees to each other. So it means in this way the current is going to flow that way. Okay, this is the generated current, EMF generated. It is usually what you call the back kind of EMF. It is going to oppose the motion that was causing it, the changing flux that was causing it. It's going to oppose, so it is going to be in negative sense, right? Now what happens here will be opposite. So at this point, if this is going in, this is coming out. It's coming out of the page. It's coming out of the page. So our thumb is out. Okay, where is the thumb is out? What's happening? The field is in this direction, and then the current is going that way. So see that the current will flow in the same direction. right? Now when this one comes here, it's the same thing. When it comes here, the current is going to flow that way instead of going down. So here you have the current going down. When you come here, it's going to go up. So you see that it will be alternating. It will be alternating current. Okay, so here it is downwards. You see it. So if this one turns and this valve comes here, instead of the current going down, now it's going to go in that direction. Okay, so this will be, so in one phase it's like that, the second phase is going to go that way, and this will be alternating current. This will be alternating current. Okay, right, so this is how the AC current is generated. Alternating current is generated, right? So you have an AC current here. Now let's use the same principle for motor. Let's use the same principle for motor. Okay. Let's see how we can have the motion. So let's, in the case of motor, so listen carefully. In the case of motor, we have two currents we have two magnetic fields interacting. That is motor. For you to have movement, you must have two interacting fields. Okay, one magnetic, another magnet. Now this is the magnet we have. Now this, we can let this have current in it. Okay, so that it also has magnet around it. Okay, so that the two magnets are going to. This is a field. The field. How this field be? We can determine the field in which this one is going. Let's say this is the red current we are supplying. Okay, let's see how it will go. So as the current flows through this, this is this. Now we are going to use what? We are using motor. We are not dealing with motor, so we're going to use Fleming's left-hand rule, 1R. So here, let's see how it goes. Now, the same principle, at this time we are using the left. Where is my current? Second current. Second finger. Okay, so it's going. Where is my field? This is external field. That's the external field. Okay. Right, now my thumb will tell me where the motor should movement. Okay, so if it is this way, you see it. The current, this is the field, F, first finger, second finger is the current flowing, and then the thumb is going to give me motion. So it means this is going to go into the page, it's going to go into the board. Okay, so if this goes into the board, what happens here? Let's see what happens on this side. On this side, the current goes like that and it comes this way, it's coming. Now the current is what? Going down, so my current is this way, that's my current. My flow is in this way. What happens to this part? This is going to come out of the page. So as this one is going into the page, this is coming out of the page. And that is a couple. Okay? So this will turn. If you connect this one to something, let's say to fan or maybe something, then it will start turning. And this is the motor action that we are talking about. It will start turning. Because this is going in, this coming. So once it turns, they are giving momentum. Okay, so momentum in between, it floats to the side. When it comes here, it's supposed to go inside. So anything that comes here, the current, when it comes here, current is being supplied that way, direct current is being supplied that way. So it will keep on moving in, and here will be moving out. And then you have the motion going that way. So this is how the motor works. So we have used the same principle for generator, and then use the same principle for the motor. Right? So once it's a turning force, okay, we are looking at rotation. So remember, the actual force in turning is what? Torque. Okay, and torque is equal to your force times what? The distance. Now this is a couple. Couple, that means the forces are in the same direction. Okay, so it becomes F times what? The distance between the two, which is D. Okay, right? The force of the magnetic field we have discussed already, or we'll come to discuss it again. So just remember, torque is this. Force can be given as what? The force on it can be given in terms of, let's say, if you are looking at the field strength can be calculated. Okay, and then you multiply by D. Let's say the force is going to be proportional to the flux density or magnetic flux density. Magnetic flux density is going to be proportional to the current. It's going to be proportional to the length that is in there. It's going to be proportional to the sine of the angle from the point. The sign of the force is going to depend on what the sign of angle and so on. Okay, and this you can put into the equation to do your calculation, right? Cool. So this is for motor. This is for motor. When it is for flux density, for this normal flux, you look at it in a different way. Right. So that is that for this calculation. But let's see. This will not work in the case of if you are looking at it like the force, the flux will depend on the density, the flux density and cause of the angle between that. So when you are looking at flux, for flux, let's say this is the magnet, okay? This is the cord here, this is the part, this is the field on it, okay? When it comes to flux, we want to see 90 degrees, the 90 degrees direction of this force on it, okay? So this is going that way. Let's say the flux is oriented in something that way, so that the actual flow here B has a certain angle here, theta. We want to find the component of this force that is acting 90 degrees on the conductor. So usually we would be looking at this in this direction. So more or less like that, okay? So more or less like this. So we have the hypotenuse here in this direction, okay? So it will cause theta is equal to what? Adjacent over what? Hypotenuse. So that your hypotenuse will multiply. This is the P. Then you get. So this is where we are looking at flux, okay? So with flux, this is what you're going to have. So that is where you can have band, okay? Okay, times the distance, So this is more or less going to give you some sort of the force is going to be dependent on the magnetic flux density there, and then you multiply by the distance as a couple and so on. If you are working out for. So you have to look at it. If it is just the torque, we are looking at the torque, then you should remember the variance equation that can be. So here, what is going to cause the motion is the flux. So if what is going to cause the motion is the flux, then we are dealing with the cause part, okay? If we are looking at the force on the body, the force on the body, the force in a particular field, okay, then not due to, let's say, a magnet or current conductor, then that one is sun, okay? Now let's look at the force on the generator, the motor, okay, there's the motor. Okay, settlement B. Okay, field, okay, goes around it. Okay, now this is the field. So then, okay, this is B. This makes an angle theta. Okay, there's 90 degrees here, and this, let's say, alpha. Okay, good. Now the force on this one, force on this. Remember that this one has current in it. There's a current in it going, okay? And this also having a field, okay? So this has set up the current in it. We can use the right hand rule. So the direction is this, okay? Yes. So you know that this has magnetic field around. This also has magnetic. So the two magnetic fields are going to interact. But remember, magnetic fields are as a result of the movement of electrons and then their direction. Okay, they are creating the magnetic force, okay? So the force this one is going to exert, the magnetic force is going to exert on this external magnetic force. The forces are the same. For every force, there's equal and opposite reaction, okay? So the forces are the same. That force is, we've already defined as F is proportional to the magnetic flux, F is proportional to the current flowing, F is proportional to the length of the conductor or wire or material in the flow. So putting all together, F is equal to what? K, B, I, L, L. Okay. Now there's another component too. F is also proportional to the sine of the angle. The sine of the angle. So this one is the B, the angle between the B and the normal. The normal to the conductor. This is the normal to the conductor. The normal to the conductor. This is the B. So the B, this angle. F is also proportional to that. Okay. Now, if we say F is proportional to that, if this is this, if sine is this, then theta. Let's say theta is what completes the angle. That is the beta, the magnetic flux density with the wire itself. With the wire itself, not with the normal. With the wire itself is theta. Then we can say F is more or less also proportional to cos what theta. Okay. So you can use any of them. So let's take this out of the equation, because we are always interested in the normal. If you know the normal, that is actually the actual force which is working. Okay, so putting all together, F will be equal to this, sine alpha. Okay, right. So when you have this will be the force on it. But by definition, if we define by definition 1 for each, okay, and then 1 Newton, K comes out to be equal to 1. Okay, so we can say that this is the same as B L sine alpha. Okay, good. So that is one way you can look at it. Okay, now the point is, if you are looking at this torque, now torque is equal to your force times the distance from the fixed point. Now this is a couple. Couple means the forces are parallel. In that case, torque becomes F is equal to times D. Okay, D, because it will have been F times D R plus R. Okay, because it will be F R plus F R, which is the same as F is. So F times what? D, which is what we have here. Okay, so the distance, let's say the distance between this. So this one force, let's say this is going inside and this is coming out of the page. This is the distance between the B. Okay, so the torque is going to be, this torque is going to be F times what? B. Right. So we can put in the equation. Let's see how things are going to be. Let's say we have a number of turns for this wire. Then we have to multiply that this whole thing by n. Okay? Right. Now this is the current, this is the length. And this is B. So length, the length of the wire, okay? So this is the length, okay? This is the distance. So the length of the wire is the length of the wire, and this B is the distance. So length times B becomes what? Area, okay? So in this case, if you put in here, if you put that one in here, you get this area, okay? And then you have your N, and then your sine alpha is coming, times your N. Of course, this will reduce to what? B, A, N, I, sine alpha. But I've said that the complement of what makes this one 90 degrees is also this one, the flux here. Okay, this one is theta, and that will be cos. So if you can also rewrite this one as let me put it up here. So if we have F, the force on the couple as F is equal to Bani sine alpha, we can also rewrite it as F is equal to Bani cos theta, okay? Where these are conflict, because we said 90 degrees is equal to cos plus sine, okay? So if this is 30, this is 60, so the same thing, they work out to be the same, okay? So it means sine 30 is the same as what? Cos 60, right? Okay, so let's see how the sine 30 plus cos 60. Okay, they will make up 90. If sine is 30, cos is 60. Okay, and that will make it up 90. Right, so these two equations can be used. Okay, so this angle is angle to the normal. Okay, and this is angle to the long axis of the wire or the conductor. Okay, so parallel long axis of the wire to the conductor. Remember that if the fields that are interacting, or the conductor is parallel to the field, okay, then of course there's no magnetic field at 90 degrees to it. And in that case, there will be no force on it. Right. Okay, so this is what we have there. Okay, so that's, hope I can clean this one. So that is for the motor. Motor is a current conductor in the field of in the magnetic field, or in between magnets. Okay. Now let's move on to the next one. The same Barney force equal to Barney principle can be used in a moving coil. Okay, the moving coil is like the motor. It's also like the motor. Okay, so the current that flows has current. The current is flowing. It has a magnetic field around it, and then we have another magnetic field set outside. Okay, the two forces interact. So the same force with Barney, either cos or sine. Right. Now this is the torque. Okay, let me put it. This is rather torque. Not force, torque. So remember, the first one is torque. It's torque here sine alpha, okay, times n, which becomes Barney sine alpha. Okay, it's torque. It's not force. Remember, the first one is for torque, because we are looking at torque as force times the distance between. Okay, right. The distance between. The distance is what is equated. It's part of the equation as b. So it's actually b. Okay, the distance is actually b. So your cos b cos becomes part of this factor, and then that brings it back to this. So that you have your length. It's the length, the b times this length, which comes back to area. That's length times breadth. Okay. So that is that, and then you can replace this one by cos theta, which is complement to the same.